Okay, chapter 3, 3.3, 3.4 is measure position. We found the center, we found how much spread or how much each deviation, each value deviates from the mean. Then we found the standard deviations and the z-scores or standardized scores literally say how many standard deviations are away from the mean. So we can translate x values into z-scores, like any one particular x value. Okay, if one data point is 86, we can figure out what that would be the equivalent in a z-score. How many standard deviations away from the mean. Okay, in one, it's a little more convenient to look at. So a z-score can be calculated by using the deviation, right? The 1x data value, and then subtract the mean from it. If it's a sample mean, subtract the sample mean, the x bar from it, and then that gets you the deviation, and then divided by the standardized deviation gives you a z-score. Okay, if it's populations, it's the x data value is subtracting the mu or the population mean from the sigma or the population standard deviation. Okay, so again, we are transforming a data point, one data point, into a z-score, so we can glance at it and say a z-score of 2.5 is 2.5 standard deviations from the mean. Okay, so for example, we have a score of 80 on a history test for a student. The class mean was 70 with a standard deviation of 10. This is the entire class. This is the population of the class. So we have an x value of 80 for just this student. And then we have the class mean, or mu, is 70. And the class standard deviation, or for the population standard deviation, sigma, is 10. Okay. She received a 75 on the biology test. The mean was also 70 for that class. All the scores averaged together. But that standard deviation for the biology test was much lower. It did not, the scores on the test did not deviate as much. Okay. The scores on the history test were much more spread out. So let's kind of get a visual on how much more spread out this was. So we're looking at the x-axis here. The mu is in the center at 70. And this one has a standard deviation for the history test. So we're going to add one standard deviation and get 80. Then we're going to add 2 standard deviations and get 90. Add 3, you get 100. And then you need to subtract a standard deviation. So you're going to get 60, 50, and 40. Okay? And then the student's score was 80, which is here. Okay, and then the biology is a little different though. The mu was 70 also, but the standard deviation is 2.5. So this would be 72.5. This would be 75. This is 77.5. Subtracting one standard deviation, you get 67.5, 65. Subtract another standard deviation, you get this. Okay, so their score is 75 on this, so that's here. Sorry, that jingling is my dog's collar, sorry. In the background there, 75 was her score on the biology test. So because of the standard deviations, they end up a little in a different place. So let's fill out what the equivalent z-score would be. Hang on a second. Sorry, I got to do something with my dog at the moment. Apologize. Back. Okay. So, z-scores, translating x's into z's. So the formula says I can do some things, but I want to lay out the z-scale here. The z-scale, there's a 0 in the center. If you scored 70 on either of these tests, you'd have a z-score equal to 0 because you scored exactly what the mean is, and there's no difference from that. But if you're up here, 1 standard deviation, 2, 3 standard deviations, and then on the minus scale is over here. Okay, 1 standard deviation, it literally means 1, 2, 3 standard deviations above, 1, 2, 3 standard deviations on the low side. Okay, so if we're following this down, up here you can tell 1 standard deviation over is this z-score of 1, but let's do the math for that. The equation up there was the deviation divided by the standard deviation. Whoops, we should use the population. Didn't mean to wipe that out. Okay, so deviation, using population deviation over the population standard deviation. So that is a score of 70, a score of 80 minus the mean over the sigma. So that's going to be 10 over 10, which is our 1. Okay? Whereas over here, it's clear that 75 is at 2 standard deviations, right? So that is a score of 75 minus 80 over 2.5. That's going to get a 5 divided by 2.5 is 2. Okay, so it matches x scores. One x value can be turned into a z-score, giving you a measure of position where that one score fell in the rest of the classes, comparatively speaking. So the question up here that I skipped right over says, on which test did she do better? Well, which test do you think was harder, or which test had the kind of the class was clumped around on this one here? And look at this. Think anybody got an A on this biology test? So it was either kind of hard, or the students did worse, or however you want to say that. But Tina excelled by getting a 75 because she did better, comparatively speaking, to the rest of the class. She did 2 standard deviations above the mean. If she'd gotten like a 76, that would be on the right side and would be an unusually high number. Okay, so the regular one, the history one, was only 1 standard deviation off the mean. So an 80 is almost an average, right? Because most of the class got lumped in within 1 standard deviation. So she did better on the bio test, comparatively speaking. Okay?